So we're still talking a little bit about HMMs, even though you already got the assignment, you already finished it. I hope you started. There was a part that I didn't get to in the calculations. I was just focusing on getting the conceptual idea, the big picture. That part is in the slides, and you could have gotten it from there, but I'm going to go over it here too, and I'm going to also rehash the whole idea of how we train an HMM. So we all know what an HMM is now, and we know the three major problems that are associated with it: the evaluation problem, the decoding problem, and the learning problem. The first two, the evaluation and the decoding, basically you're given a model, and you're given a set of observations, and you're asked either to evaluate the probability of that observation according to the model, or to decode the most likely hidden state sequence according to the model. In both cases, there is one clear, unique solution, and you're going to find it. It is a solved problem. And not only are you going to find it, you're going to find it in polynomial time if you calculate things cleverly using dynamic programming. Okay? That's the first two of the three problems. The third problem, we're not as lucky. So as part of solving the first two problems, especially the first one, the evaluation problem, we calculate a quantity which we call the alpha quantity. And it has two indices, one over time of the observation and the other one over states. And I always forget which one I put as a subscript and which one I put in there. So at least this time I will follow what the slides say. So here the index would be t, and here it would be I. And it's defined as the probability of observing the first sequence, the initial substring, O1 through O sub t, and at time t being in state I, given the model. We calculate this. This is relative to a particular model, namely to a particular set of parameters, A's and B's. Right, the transition and emission probabilities. This depends, the actual values depend on the A and B. We also calculated something we call the beta. It has very similar indices, and the way we calculate this is with a table. A two-dimensional table, and we scan through it starting on the left and t equals 0 and building column after column in a recursive fashion. This is what allows us to do it in the polynomial amount of time. Polynomial amount of calculation was n squared times t steps.
The reason why we're seeing this.
Similarly, we calculate the beta table by going backwards. And beta is defined a little differently. Beta sub t of state I is defined as the probability of the final substring starting with t plus 1, ot plus 1, ot plus 2, through O big T, conditioned on, notice that this condition is now in the conditioning part, at time t plus 1 being in state I, and the model. And this also depends on the model, which is A's and B's, and also takes this amount of computation. Now we're going to the third problem. The third problem is the learning problem. The learning problem says that given only big O, some long set of observations, find the set of parameters that maximizes over all possible parameters the probability of the data given the parameters. So this is the standard maximum likelihood framework. Given the data, adjust the parameters to maximize the likelihood function. Except the maximum likelihood function, the likelihood function is very complicated. We cannot solve this analytically. We cannot come up with analytical values. And that is why we use an iterative procedure. And it is an EM procedure. And I give you the essence of it. I define the ZIs, EM. The Z, they're not ZIJs, they're T, ZTI. T is the index over our training examples. We have O1 through O big T, in general OT. I, actually, we're going to have both I and J, right? ZTIJ is going to be the random variable that gets 1 if and only if Q sub t is Si and Q sub t plus 1 is Sj. So it basically captures the hidden event that at time t we're in state I and we're transitioning next to state j. And it's 0 otherwise. The likelihood function can be expressed as a member of an exponential family with these Zij's. I'm not going to show it, it's very hairy, but I'm going to state it and say that therefore the only thing we need to care about is the expected values of the Zij's, ZTIJs. And I also said last time that I'm going to define a variable called, is it eta or zeta? It's that one of these squiggly variables that I can never write properly.
The name of that is Xi.
Xi, thank you. Xi. And how do I do it? I just do to the right, to the left, and then a few more times? I'm sorry? Xi.
Yes, so it can be read either Xi or Xi.
Do you know how to write Xi?
It's like euro, but there is
Okay.
also a symbol like zeta. It's a little bit like less. Like,
I know, I get horribly confused.
yeah, that's just a squiggle.
So Xi has one more squiggle than Zeta.
Okay, so let there be as many squiggles as are necessary here. Psi T I J is going to be the expected value of Z T I J. I think I wrote it a little differently last time. I called this Joe, I think. But let it call it Z. It's more in line with the standard EM terminology. And remember that expectation of a binary variable is probably the probability, is basically the probability of that random variable being 1. And I said that I'd really like to derive these things for all values of t, I, and j, because if I do, my re-estimation of the parameters of the model can all be expressed in terms of these psi values. Remember that? I will write them again. I will treat these psi values as if they were not expectation of something unknown, but as if they were actually this many fractions of a data point. So for example, the transition probabilities, so I'll write here the re-estimation. Aij, my new Aij, my new estimate for the transition probability from I to j, ideally should be the number of times I observed I going to j divided by the number of times I observed I going to anything. So if I had access to the hidden data, to the hidden sequence, I would calculate this, and this would be my maximum likelihood, my relative frequency, and therefore maximum likelihood estimate of Aij. But I don't have that. The best thing I have is an estimate of that in the form of the fraction of each t, of each time point that I attribute to this transition from I to j. Or in other words, the probability that I think the transition from I to j actually happened at time t. So I'm summing over probabilities rather than over actual zeros and ones. So this would be summation over all t of psi t I j. This would replace this. And the denominator would be replaced by summation, by the same thing, summation over t of psi t I j, but also summation over j, since I don't care into what I changes. I just want to care about I being there. So I take, if you remember, this is the general formula for EM, the shortcut for EM in the case of distributions that come from, likelihoods that come from the exponential family, is that you define these z's, and then you go directly to the maximum likelihood formula, pretend that you had the true hidden events. That's what I did here. If I knew the true hidden events, what they were, I would just count them and divide. And then I substitute for the actual counts the fractions that are expressed by the expected values of the z's. So this is re-estimation of the transition. The re-estimation of the emission, Bj of some O. Originally, if I had access to the data, it would be a sum over the number of times I was in state J and output T was O, divided by number of times I was in state J. Please try to shut as much as possible. I would simply count how many times the system was in state J, and of those, I will count what fraction of the time it emitted symbol O. I do know when the system emitted symbol O, but I don't know if it was in state J or not. So as a result, this will change into zeta of T I j summed over all t such that O sub t is O. There's no point in summing over positions where the output was not O. We know that's out of the story. We're only summing over positions where the output is O. And we're going to sum here also over, I call this J. That's probably not very consistent of me. I'll call it I. Sorry. Doesn't matter what I call it, but I want to use the same notation here. So I'll sum here over J. The only important thing is that this is I. This is the same I. And then maybe I should have started with the denominator. It's easier. This is a summation over all J and over all T of psi T I j. This time I don't restrict myself to positions where I observed O, because I want to sum over all the time points where the system was in state I. So I sum over all possible J's, because this is transition from I to J, and all possible positions. So by having this one thing, this one psi, by summing it in different ways, I can calculate the necessary expression for maximum likelihood re-estimation of the A's and B's. Jeffrey?
Under the second summation.
Here, a mess is the answer. I have a mess here.
Would it be actually a little bit...
One second, let me just finish this answer. It's T such that O sub T, let me just write it like this. O sub T is O. So this is the O I'm interested in. Let's call it O star. And it's a particular value of the output. I want to know the emission probability of O star in state I. So if I knew everything there is to know, if I knew all the hidden events, I would count the number of times the system was in state I, and of those, what fraction of the time the emitted symbol is O star. And if I don't know, I just substitute the summation over all T such that the output is O star. Yes.
I think I thought that there would be only one T plus, but it's not correct.
Okay. All right, so far it's just a repetition from what we did at the end of last lecture, yes?
Just to check, the first sum is over J?
Here,
Yeah.
it is over J, yeah. I changed this to I.
Yes.
Yeah, first sum is over J. Sorry, I am a mess. I'm sorry? Okay. All right, so all this is a repetition. So hopefully I convinced you that if you had these psi guys, which have 3 indices, so you need to know them for every t, every I, and every j, you can re-estimate the parameters. The only thing I haven't shown you yet is how you get these psi guys from the alphas and betas. So I'll show you that, and it's on the slides. Hopefully you've seen it already. It's a very nice visual argument. It's not worth firing up the projector for this, so I will. I want to calculate the following. E psi t I j is equal to the probability that at time t we transition from state I to state j. So at time t we're in state I, and time t plus 1 we're in state j. All right, so I will call it I to j t to t plus 1, conditioned on seeing the full observation sequence and knowing the model, some tentative value of the model. This is the definition of what we're trying to calculate. I can rewrite it as the probability of this I to j, t plus 1, and O, conditioned on the model, divide by P of O, conditioned by the model. Is this right? Divide by P of O times P of this given O. Yes. Right, so if you move this to here, you can write this joint probability as first the probability of this part given the model, and then the probability of the second part given this in the model. It's chain rule. So now I'm going to focus on this part. This part, by the way, is the solution of the alpha table. To explain, I need to explain the entire data and doing exactly this. I don't care what else I did. I don't care where else I was before time t or after time t plus 1. But I do want to insist that I'm at time t at state I and time t plus 1 at state j. So I will come here. This is time t, this is time t plus 1, and these are other times. I will come here from any state possible. So these are the states S0, da 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 da. This is state Si, Sn. I arrived here at state I, and then I transitioned into state j. And strictly speaking, it's not in the same line because if I listed all the states here, so maybe it's a little bit to a different state. And then from here, I transition to wherever. And I have the O1, O2, da 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 da, O sub t plus 1, all the way to OT. To explain, I need to explain all of this and being here and being here. How am I going to do it? I'm going to put together the right values of alphas and betas. I'm going to first account for all the values of O1 through OT with alpha sub t of I. So this explains coming up to here and being in state I. Then I'm going to explain transitioning to J by using the transition probability AI to J, AI to J. Then I'm going to explain being at time t plus 1 in state J, and emitting symbol OT plus 1. So I'm now explaining this symbol, OT plus 1. And now, given that at time t plus 1 I'm in state J, I'm going to explain the rest. Given that at time t plus 1 I'm in state J, I'm going to explain the rest. So that would be beta t of J. Alpha t of I, Aij, Bj. This claimed that it should be beta t plus 1 of J. By definition of beta, oh yeah, time t, this is time t.
I think if you said beta T of J.
I was wrong here. I was wrong here. The definition of beta is accounting for the observables from t plus 1 on, but the time t being in a particular state. And therefore, this would be t plus 1. Because I already accounted with this A and this B, I accounted for the transition from here to here and the emission of this symbol. And now, by using beta of t plus 1, I am accounting for symbols from OT plus 2 and on. So I just glue it together, and the alphas and betas are defined not identically because of that, because we knew that we would want to put them together.
Is the beta, big beta table accounting for emitting symbols afterwards, or?
Not beta, no, this is B. So there's a big difference between A, B, and alpha beta. A is the transition probabilities. B is the emission probabilities. Alpha and beta are a different kind of creature. They are cumulative calculation based on dynamic programming
And
that take into account lots of different things, multiply them together.
So the alpha table, right, takes into account the probabilities of getting to state Si at time t.
Alpha does.
Right, and then the beta table accounts for all the possible transitions away from state J
No.
after time t plus 1.
No, beta table is defined this way. It calculates the probability of the remaining output conditioned on having started the time t in a particular state.
So the probability of having that exact output given that you started at
Yes.
state Sj. Okay.
So alpha and beta are defined in terms of your particular outputs, particular observables. One accounting for the first initial part up to some point, and one accounting from that point on. A and B are the fundamental parameters of the HMM. So it can get complicated with alpha, beta, A, B, and other Greek letters that are hard to pronounce. So let me put the whole picture together here. You start with some model which consists of the A's and the B's, also known as small a and small b's, Aij and Bio. These define the model, define a tentative model. Use that to calculate alphas and betas, alpha and beta tables. You're using this and also using O. Use that and the observables O to calculate the alpha and beta tables. Alpha and beta are tables, so they are also, this is T by N by T, and this is N by T. A is N by N, and B is n by the number of observables that there are. If the observables come from a continuous space, it's not a discrete distribution, it's a continuous distribution. So we started with some model. We use it to calculate the alphas and betas. Then we use the alphas, betas, in combination with the A's and the B's to calculate what? The infamous xi's or chi's or whatever they are. And the chi is a triple table. It's T by N by N. Has 3 indices. And what's the last thing we do? We re-estimate the A's and the B's in terms of the new psi. This is the M step, because it uses things like this, which maximize the likelihood under this assumption.
So the E step is calculating the psi table?
Yeah, this is the E step, but you first have to calculate alphas and betas and then calculate that. So all of this together is the E step. And this is the M step. I didn't put indices on these, but if you start with some lambda, call it lambda sub 0 or super 0. You can also call the A super 0 and the B super 0. And the A's and B's here also all have a 0 index to them. And then the general iteration is that you calculate alphas and betas that are, what index did we use for iterations? K. That are k based on gamma k. So I'll put it only here. This would be sigma k because it is based on model. I'll write it here more explicitly. Use lambda k use lambda k and O. O is fixed. The observable is fixed in this process. This is fixed, doesn't change. It's big O, right? This changes every iteration. So in every iteration, you use the current set of parameters. Remember, this means A's and B's, transition and emission. To calculate new alpha tables, you can put a super index here of k. And then you can put a super index here of k on the zeta, on the chi, sorry. And then you re-estimate these. So you re-estimate, it becomes the new lambda. And this lambda is k plus 1. All the indices are in the slides. You don't need to worry about them. I'd rather you focused on the understanding. Questions? So whatever we know about EM in general holds for this particular EM, which means from iteration to iteration, the likelihood of the data under the model is guaranteed to increase, or at least not decrease, generally increase. So if we calculate the likelihood of the data under the models, it'll be an increasing value with each iteration. How do you calculate the likelihood of the data? It's the evaluation problem. Remember, that's the first problem we solved. So if you calculate P of O given the first model, and then you calculate P of O given the model after the first iteration, and you keep doing that, P of O given model of iteration K, these numbers are guaranteed to never go down, and in reality they will always go up. And this would be your criterion for when to stop, when they don't go up much anymore, when they start going up by tiny amounts or almost not at all, basically converging. Is it guaranteed that they will converge? They're guaranteed to go up, but are they guaranteed to converge? Do you remember the condition?
They should converge.
They should. What if they don't want to?
No, because it's a convex function with a lower bound of the original.
Say it again.
Isn't it a convex function which is the lower bound of the original function?
I don't think it has to do with convexity, but there is one other condition, and there's a likelihood function should be bounded. So in non-decreasing sequence, this here is out from calculus, a non-decreasing sequence, namely a sequence that either increases or stays the same, which is bounded, namely there is some level above which it never goes, must converge. A non-decreasing function that is not bounded does not have to converge. It can go up and up and up and up and up and up. So will this converge? The answer is depends on the specific form of the likelihood function. The likelihood function that we use to calculate is a large summation, a large but finite summation of a lot of products. And the products are alternations of transition and emission, transition and emission, transition and emission. The transition probability is always bounded, because it's a probability, it's between 0 and 1. The emission probability may or may not be bounded. If the symbols are a finite set, or if they are from a discrete set, then of course it has to be a probability distribution, it has to be bounded. But if the emission is from a continuous set, then what we have there is not a probability, but a probability density function, and the probability density function may not be bounded. So you need to worry about that if you're representing your output, your observables, in a continuum. Yes?
Follow up on the question of an output space which is a continuous distribution. Supposing you were to model your output space as a Gaussian, how would you learn your parameters from the EM step?
Yeah, excellent point. So you would have a bunch of points with their fractions, a bunch of observables, each with a fraction. And you would ask yourself, what is the best way to learn a Gaussian from a set of fractions of points? And it's very similar to learning it from a non-fraction set of points. But you want to restrict your variance to not be less than some level. But if you have more than one data point, I mean, you may not need to do that, but you might want to do it just in case so that you don't. If you do a mixture of Gaussians, that's a problem. If you do a single Gaussian, it's not so much of a problem. So subject to the restriction, the likelihood is bounded. This is guaranteed to converge, and it's guaranteed to converge to a local maximum. And it will not be a global maximum. And in general, in HMM of any size, any reasonable size, you're not likely to get a global maximum. So there are situations where EM runs in a convex likelihood space, and therefore you will get the local maximum. There are situations where you do non-convex optimization, and there aren't too many maxima, and if you try hard enough, you will find one. But in HMMs, usually the case is that there are lots and lots of local maxima, and you can notice that by starting this EM procedure at different initial conditions, and you'll end up in very different final conditions. So it just gives you a hint that there are probably many, many places you can get stuck in. And you can even get a sense of how diverse the space is by starting 1,000 times or 1,000,000 times to different places and see how many times you end up in the same area. That's called being in the same basin of attraction. right? The point you start can be thought of as falling into a basin of attraction that will pull you into a particular local minimum, and or local maximum, and if the likelihood function looks like this, then you'd end up in many different places. And if it looks only like this, then you'll end up in only 3 places. And in HMMs, it usually looks much more like this, only much worse because it's very high dimensional. So in HMMs, we do have a serious problem of finding a good solution. Running EM will give us a local maximum, but it won't necessarily be a good one. The area where HMMs have been used, one area where they have been used extensively is speech. And in speech, we run these algorithms all the time to train acoustic models. And if you just start from random or flat acoustic models, flat HMMs, you're not going to get a very good point. You need to build it very gradually, and if you want to train HMMs in one language, you start with HMMs that were built for a different language, and you use it as the starting point. I mean, it's a vast field to search in, and you don't want to start from nothing. HMMs are used in so many places. They're used in vision, they're used in planning, they're used in reinforcement learning, and they're used all over the place. When EM is applied to HMMs, it goes by the name forward-backward algorithm. It's called forward and backward algorithm because a lot of what you do is calculating these things, so this is called the forward table and the backward table. Historically, the forward-backward algorithm was formulated and published before the EM method was published. So it was published as a special case for HMMs, and then the people who came up with EM said, hey, there's this generality to this, and several other algorithms have been used, and generalized it to the most general case of EM. But this came around before.
So is there like a 30-year difference between those two events?
Yeah, so EM was in the 70s, Dempster, and so EM is 70s, and forward, backward, maybe 20 years, I don't know exactly. Do you remember the dates?
No, I was just wondering.
Yeah. The people who wrote the EM didn't say that they invented it, they just said that there's this method that's been used all over the place in many different situations. Here's the commonality, and here let us prove that it always works in these situations. The critical element of proving here was proving that the likelihood never decreases from one step to the other. And that's done using the Jensen inequality. This is the crux of the proof.
So I have another question. So it's only the case that the likelihood is bounded, then EM will achieve global maximum, correct?
No.
Local maximum.
No. If likelihood is not bounded, EM may not converge. If likelihood is bounded, it will converge, but it will converge to a local maximum, not necessarily a global maximum. The only time it's guaranteed to converge to a global maximum is if the likelihood function is convex, namely it has only one maximum.
Okay.
Question?
Actually, even if the likelihood function is bounded, it may not have a maximum if it increases and infinitely.
Increases?
Like
You mean asymptotes?
Yes.
If it's not a closed, if the parameter set is not closed, I suppose so, yeah.
Yeah.
But it comes arbitrarily close to it. There's another issue that you need to be aware of. What's guaranteed to converge in EM under conditions of bounded likelihood. If the likelihood is bounded, the likelihood of this sequence is guaranteed to converge. It doesn't mean the parameter values will converge. So we can be in a situation, imagine the likelihood surface in a two-dimensional parameter space. So it'll look like a mountain. This is a two-dimensional plane, and the mountain blew off its top. There was an explosion, and the top was blown off, so this is flat here. Now, the parameters are x and y. The likelihood is z. Okay? So this is likelihood, and the parameters are x and y going into the board and sideways. We can climb this using EM or using, you can even use gradient descent to climb it. And you can get to a point here where you can circle either inside or on the periphery, where the likelihood function stays the same, but the parameters keep changing. This is called an attractor. And a EM can get stuck in an attractor where it keeps changing the parameter values, but the likelihood doesn't increase. So often people in practice look at the parameter values to see do they keep changing. And when they stop changing much, they stop. And usually in practice it works, it's not a problem. But theoretically you should not look at the parameter values. You should look at the likelihood function and stop when it stops increasing significantly, when it converges, rather than when the parameters converge. People look at the parameters because it's easier to look at the parameters than to calculate. You know, remember that calculating this means recalculating the alpha table.
I was just wondering if every HMM has that sort of shape, the likelihood of every HMM is that sort of shape, or there are HMMs which have, say, relatively lesser local
Yeah, I don't know. I wasn't making a mathematical statement. I was making a practical statement about, in practice, when we use HMMs and the problems I'm aware of, vision and speech and others, usually you have this problem.
And really it's too high dimensional to realize.
Yeah. Your assignment is really nice. You may be frustrated because it forces you to understand the little details because you have to code them, but once you code them and they work, you feel, I think I mentioned before, you feel like, I get it now. And it's almost impossible to get that feeling without banging your head against it enough. Okay, are we ready to move on? Okay, so we're going to move on completely. We're going to talk about how to combine different types of evidence or different information sources into a combined model. And I'm going to use an example, a very simple example. Suppose I'm still in the context of predicting a word from a history, but what I say is very, very general about any other kind of model, not just for language. I'm specifically interested in predicting the probability that the next word is the word bank. Condition on history. And I would like to consider two very different sources of information. One is what was the last word of the history. So I'd like to contrast the probability that the next word would be bank, knowing that the previous word was the, wi minus 1 was the, with the same thing if wi minus 1 was 2. No, not good, because you can say to bank. Humpty? Okay, Humpty is good. So what I'm after here is a very strong syntactic constraint. It's not likely that after Humpty you will have the word bank. But after the, you may very well have the word bank. And now I want to consider a different source of information. So this is syntactic. Here I'm going to have semantic. Probability that the next word, I'm just going to write it P of bank, meaning probability that the next word is bank, conditioned on somewhere in the history there was the word account. Or some other bank-related word, interest or teller. Maybe teller is nicer. And I want to contrast it with the same probability of the word bank, given that I'm told that the word teller definitely did not occur in the history. Maybe to make it symmetric, I will make this just not the. Not the. So I have two binary features. One that tells me whether the last word of the history was the word there or was not. And that's more of a syntactic source of information. And one that tells me whether the sentence had the word teller in it or not. If I had only one of these sources of information, how would I estimate the probability of bank in this condition? I would use relative frequency from my data. I will count how many times the word there occurred in my data and the fraction of them that were followed by the word bank, and compare that to how many times the last word of the history was not there, was anything else, and what fraction of that time the next word was bank. Right? I'll just break it very neatly into two. In fact, this is what a decision tree does. A decision tree that tries to capture this information will have a simple node that asks, is the last word the? I keep hiding my stuff from myself. A decision tree here would say, is wi minus 1 equal the? Question mark. And if the answer is yes, I will give an answer here. And if the answer is no, I'll give an estimate here. And similarly here, a decision tree will ask, is the word teller in the history? In the history. And yes and no, I'll get different answers. If you remember, I had a view of the history space based on questions asked by a decision tree. There was a space of all possible histories. All possible histories. And this question divided it in two, not necessarily equal parts. I'll call it Q1. Q1, this is the yes side, this is the no side. Remember that view? Whereas here, it would be a different, it's the same space, but it's a different question. Call it Q2, and it divided into a yes or a no. Now, suppose I want to benefit from both questions. In the decision tree framework, I will apply Q2 here, with a yes side and a no side, and I will also apply it here, Q2 with a yes side and a no side. I now fragmented my data into 4 parts based on the 4 different combinations of answers. Answer to question 1, answer to question 2. And that's a fine thing to do with 2 binary features. But if you have 100 binary features, that will tend to fragment your data very, very fast. Namely, if you stopped after 2 questions, you will now provide the answer. So it'll be ask here Q2, and again ask here Q2. Of course, you don't have to ask the same question in both, but let's say you do. And now you have 4 terminal nodes, 4 leaves, and you calculate and estimate the relative frequency for each one of the 4 different conditions. And that corresponds to calculate the relative frequency of the word bank here, the relative frequency of the word bank here, here, and here, separately. When I say you fragment the data, what I mean is that as soon as you ask the first question, you irrevocably broke your data into 2 parts that now don't influence each other. And then you ask the second question, you broke it again, and now you have 4 non-communicating chunks of the data. You partition the data into 4 chunks, and each chunk is used to estimate one thing. And again, if you have a lot of data in just 2 questions, that's not a problem. But if you have a lot of data and 100 questions, 2 to the 100 is a very, very large number. And you can see it when you build your decision tree that very quickly the amount of data on which you make decisions and the amount of data on which you make your final estimate of the probability of the word bank is very, very small, and therefore its variance becomes very large. This is known as the fragmentation problem. And every partition-based model is vulnerable to that problem. It suffers from that problem. Question?
Yeah, regarding the division in the binary tree wall, at least like in my experience from the whole war, if you divide it like using one word, or like, especially if this word is infrequent, this is essentially like a useless thing to do because the conditional entropy like almost remains.
So you're talking about questions that chop off just a little bit of the corner?
Yes, right. So,
Okay.
And like,
So the example I gave may not be a good one.
okay.
I did not mean to suggest questions that chop off just a little bit. You could use them, but you could imagine two questions that, for example, this is not that little because the fraction of the data, 5% of the data is there. But I can break it down by whether the previous word was a noun or something else. And I could break it here by whether the history contained one of the 50 terms associated with banking. And now it's not that rare. Okay? The principle will still apply. I have two conditions that are very different. They consider very different sources of information. And one thing I can do is fragment the data to model them jointly. If I do that, it's called joint modeling. It's like building a table here it says hi minus 1 is the, and here it says wi minus 1, and here it says wi minus 1 is not the. Here it says teller is in the history, and here it says teller is not in the history. And now I can write here the counts of how many times I observed the word bank. C of bank here, and here, and here, and here, and how many times these things occurred and normalize them properly. This is like calculating the probabilities of a 2x2 table directly. And it's okay if you have a lot of data and just 2x2. But what if you had a 2x2x2x2x2x2x2 going 100 times? Then you have too many cells. And now you need to make some simplifying assumption. If you have 100 binary features, fully modeling it will take on the order of 2 to the 100 parameters. And that's way too much. The assumptions we usually make are some kind of linearity or separability assumptions. We make an assumption that the features don't cross-talk, or there's no interaction between them. But that's not very well defined. We need to define exactly what we mean by no interaction between them. So one simple assumption we can make is linear in the space of probabilities. We can say that the probability of bank is a linear combination of its probability according to the different features. So P of bank given the history is lambda times P of bank given whether or not the last word I minus 1 is there, plus 1 minus lambda times the probability of bank depending on whether or not the word teller was in the history. I basically build two different predictors of bank. One that only looks at the last word of the history, and another one that only looks at whether the word teller occurred. In fact, I can build many, many predictors. I can build, to answer your question, a a predictor that does not depend on it being the word there, but just a bigram predictor, P of bank given whatever the word before is. Just a bigram model from my data. And I can also build a P of bank given all the content words in the history. I can build some model that looks at the content word further in the history and tries to get a sense of, is this document or is this sentence about banking? And then I can combine these two with some lambda and 1 minus lambda. Right? And I can do it not just with 2 components, I can do 100 components. And I can combine them linearly. And how do I choose these lambdas? Held out data, like the algorithm that you guys implemented. That's a fine thing to do. The nice thing about it is that it results in a consistent and normalized model, because if I have a bunch of specialized predictors, P1 through Pk of the same thing, of the word bank, given something, and I combine them with lambda, so it'll be lambda 1 through lambda k. As long as the lambda is summed to 1, this is a shrinkage. This is a linear interpolation of multiple probability models. As long as the original component predictors are bona fide probability distributions, and the lambdas are between 0 and 1 and sum to 1, then I'm guaranteed that the combined result is also a probability distribution. So that's on the positive side. On the negative side, linear combination of probabilities doesn't always make sense. I deliberately chose this example of bank and the, because after the, we expect nouns. Maybe adjectives, but likely to get nouns. After a verb, we don't expect nouns. Right? In English.
You can have plural nouns, but
Right. Singular noun. I don't expect singular noun. But the main point is that syntactic constraints can be very strong. Whereas this model that looks at the semantics, at the content words further back in the history, is completely blind to local issues. And it basically just tries to guess whether the topic of this sentence is something to do with banking or not, or something else. Now, if I just combine these two, if I assigned a reasonable weight here, I don't know, 30%, that means that even when the last word syntactically made it incredibly unlikely that the next word would be noun, it would still get 30% vote for that noun. This is a hand-waving argument, and there may be a way of making it more rigorous, but the point I'm trying to get across is that by using linear interpolation, you're pre-assigning each component their own part of the mass, lambda and 1 minus lambda, and you're allowing them to vote independently, or to put their vote independently into the mix. Whereas what I'd really like to do is I'd like to take, say, the baseline probability of bank, go to the semantics component, and say, do you think this is about banking? If you think it's about banking, I will crank up the probability of bank by a factor of 3. If you think it's not about banking, I will crank it down by a factor of 50% or something. Then I'll go to the syntactic component and say, do you think a noun is possible here? If you're telling me that for syntactic reasons it's not, I'm going to crank it down by a factor of 10. I'm not going to say it's impossible, but I'm going to say it's highly unlikely. And if you think it's very likely here, I'm going to crank it up a bit. What I want these experts to do is to make relative corrections rather than absolute corrections. If I didn't convince you, it's because I'm hand waving, and maybe I just didn't hand wave properly. I'm not giving a mathematical argument, and in fact I cannot prove that what I'm suggesting is better, but I do claim that it is better for language for the kind of features that we're considering. And in many other cases it's better. So what I'm arguing for is having the different components contribute a relative amount, a bumping up or down, rather than an absolute amount. So what would this bumping up and down look like? No, this is related. This is not. I know, but I don't know if it looks. Okay. I would like my probability of bank, given the history, to consist of some baseline, which is probability of bank unconditional on anything. So if I don't know anything, this is my baseline, my unigram probability of bank. And I want to multiply it by some factors having to do with the contributions from, there are bump up or bump down factors. They're increased by this percent or decreased by this percent. So this factor would be, I would call them, what do I call them? Mu's. Mu of how the word the tends to cause bank, if it follows right after it. And also a factor mu for how the word teller tends to cause the word bank to show up later. I put an arrow here to show that it's later in the sentence, whereas here I put a comma to show that it's immediately after. But these are basically factors. And I may have one factor if this is, if there was, I'll do it this way. Since the situation here could be either the last word was the or not the, I could have two such factors, mu of the and mu of not the, followed by bank. But I will fold one of them into my baseline. So I will leave here only the ratio between the two. My baseline is somehow an average of these two situations, right? Sometimes there is the, sometimes there isn't the. And I'll do the same thing with the second part. So what I end up with is correction factors. And I can say that these kick in only when the appropriate condition holds. So mu is some value, let's say 2.3, if the last word of history, wi-1, was indeed the, and it's 1 otherwise. 1 is the no-op. Because it's a product, multiplying by 1 is like not multiplying by anything. And the same thing goes for this one. This is mu the to bank. This is mu teller to bank. And this might be 5 point something if teller was in the history and 1 otherwise.
I have a question. You mentioned cranking down the value because not having something is also a useful source of information.
Mm-hmm.
Right? But if you multiply by 1, this is not.
Right, so I was running a little fast, so let me not run fast. Let me take a step back. Really what I want is to multiply down, so it will be 0.8 here. Okay? And the same thing here. This will be 0.3. So there would be one of the two numbers will be a bump up and the other one will be a bump down. I'm going to make my computational life easier by saying if I'm going to multiply by either 2.3 or 0.8, let me pre-multiply by 0.8, and then if this is true, I'll divide by 0.8 and multiply by 2.3. So I will just look at the ratio between these two. I was just using a trick to say that if you're going to multiply by one of them, might as well fold one of them in and leave only the difference. But this is really the right way to look at it. You're either bumping up or bumping down. I think it's a clear way to look at it this way, so I'll leave it like this. In general, my function would look like this. It would have some initial value. This is not meant to be xi. But then you'll have a product of these mu values. I goes from 1 to n, if you have n such features. And one way of writing this thing is to say that mu I is going to be raised to the power of f of I of the history and the word, where f of I is 1 if and only if this feature holds, if the word the was before and the word bank is the next word, and 0 otherwise. So the fi's are indicator variables. They're either 0 or 1. If they're 0, it's as if the mu I wasn't here, because mu to the power of 0 is 1. If they're 1, the mu is there. So I'm now using the trick that there's only one mu, and it only kicks in. Am I confusing you? Oh, done.
You just write mu equals 2.3 instead of putting in if and otherwise there.
Yeah. Well, if I write,
Because the if and otherwise are in the f's, so the mu is just a number.
right. The mu is a number. The mu in this case is, well, it's this number or this number.
Yeah, I mean, you
But-
can keep the mu's, but you define the mu's as just a number without a branch.
Okay. Yeah. Thank you. But, okay. All right. Since all of this is hand-waving justification, you can just, even if you don't follow me, you can just continue from this stage. So what this stage would do is it would define by probability distribution, this one, P of bank, P of word, P of an H, as something that looks like a product of bumping factors. Some of them bump up and some of them bump down. I'll redo the whole thing and reassert that you don't need to have understood the previous part. An exponential model is a conditional exponential model is one that looks like this. Product of mu I, f of I, of h and w. I goes from 1 to n. And there is something here that does not depend on I or mu.
You don't have to put it here. That can be absorbed into the mu's. You can define one of the f's as 1 if the word is bank and 0 otherwise.
Right, let me just write something here. This is how I define an conditional exponential model, where f of I of h and w is usually an indicator function that takes on the value 0 or 1. It will take on the value 1 for some conditions of h and w, and otherwise it'll take on the value 0. And you can just take it as a definition without any of the hand waving about bank and so forth, but I'd like you to develop that intuition. So this would be 1 for some conditions, and 0 otherwise. Incidentally, it doesn't have to be a binary feature. It could have any discrete or even continuous values. But we're going to mostly think about it as a binary indicator variable that picks up situations and by being 1 and is 0 otherwise. Now So this is the mathematical definition. That's really all you need. I'd like to bring back the intuition. The idea is that the probability of a particular word for a particular history is given by a product of a bunch of bumping factors that are relevant to that combination of word and history. So if teller and bank are related, there may be a bumping factor correlated to that. There will be a particular I that is specifically to the relationship between teller and banker. And it would be a positive number because it would tell you by how much, by what factor to increase the probability from the situation where teller was not there to the situation that teller is there. So that difference would be 5.3 divided by 0.3 is actually more like 17. So the bumping factor would be 17. It's how much you change from the situation when it's not there to the situation where it is there. This part is a normalizing constant. Because this is a conditional distribution, the normalization constraint is that for any particular value of h, summation over all w's must sum to 1. So that normalization constant is a function of h. Different h would have a different normalization constant. So all of this was to argue why I want my function to look like this, why I believe this is a better way of combining features than by linear interpolation of individual predictors. Now, there's another way of looking at it which might be even easier. Try to look at the log probability rather than the probability. 1 second, Malcolm. Log probability of word given h is negative log of z of h, that's constant for a fixed h, plus log of this becomes a sum of fi of h and w times log of mu. Instead of log of mu, I will write lambda I. I'll write here that lambda I is defined as log of mu of I. Or equivalently, mu of I is defined as e to the lambda I. So whether I express my model in terms of mu's or in terms of lambdas completely doesn't matter. It's just a log transformation. The parameters of the models are mu here or lambdas here. So the result that I got is that the log probability, according to an exponential model, is a linear combination of the parameters lambdas, and it's a linear combination based on the value of the feature functions. Or alternatively, that the log probability is a linear combination of the feature functions, each weighed by its appropriate parameter lambda. A more important feature will have a larger lambda because it will correspond to a larger mu. A larger bump up is a larger mu, or bump down. Whether it's up or down will determine whether the lambdas are positive or negative, right? A bump up means mu is larger than 1. Log of mu, namely lambda, is positive. A bump down means mu is smaller than 1. Log of mu is negative. Large absolute values of the lambdas mean that the feature makes a big difference. When the model is viewed this way, it is called log linear. It's kind of a strange terminology. What it means is that the log of the model is linear, not that the model is log linear. The log of the probability is a linear combination of features. So log linear model and exponential model are the same thing. Yes?
So what happened to the unigram probability of our word? Could you just extend it and say you have a feature function that's always 1 and the mi is just...
You could. So what would happen to the unigram probability, namely when, well, it's not the if none of these features are on, it doesn't mean that it's the default case. because the default case, they could be on, they could be not on. If none of them are on is a particular case when nothing is on. So think about it as a hypercube. But not in 3D, but in n dimensions. The value of each one of the n features is either 0 or 1. So the values of all the features correspond to a particular corner of this hypercube. And the situation where none of these mu's kick in corresponds to the bottom where all the values are 0. It doesn't answer the question of the unigram.
But I was saying earlier we motivated this
Right.
starting with the unigram,
Right.
having a pumping factor.
Right. But I got rid of that unigram because I took the bump up and bump down. I took the bump down, put it into my baseline, what used to be a unigram, and changed the bump up into the ratio between the two. Right?
That didn't answer the whole question.
Let me just hold it 1 second. Let me just try to answer what you're saying. I had a baseline, and I could multiply it either by 5.3 or by 0.3. These were my two values. What I chose to do is I chose to fold this into here. So my new baseline was the original baseline times 0.3. And then I will only consider either to multiply it by nothing or to multiply it by 5.3 over 0.3. This will result with the same two possible outcomes. And I did that for each one of my features.
Right, but what's the baseline in
Yes,
that particular
his question
form?
is where did that?
Oh, I don't know what it is. To find it, I will need to sum over all possible histories in certain proportions. I'm not doing that there. I only used it there to argue for the form of the function, that I want it to be a set of bump up and bump downs.
So in this particular case, in the most general exponential model, your baseline is actually just another feature.
I don't think I have a baseline, but Yun,
So,
did you?
one of the way of understanding this is treating that baseline as a weight or as a mu, and the corresponding feature is 1 if the word is bank and 0 otherwise.
Okay. Would that get, 1 second, would that get the right value? Yeah, when we discuss how we set those lambdas, yes, it will get the right value. But I don't need it explicitly in the model anymore.
Yeah. So,
I do not need the model unless I have.
yeah, because this is not general enough. You are still starting from the unigram, and in the more general case, you can choose not to have those unigram probabilities. That's more general features.
Okay, I'm not sure we're disagreeing. All I'm saying is that I started with this as a way of explaining why I have a bump up and bump down. But once you accept that I want to present my model as a series of multiplicative bump up and downs, I no longer need it. I just present my model this way, and then it boils down to just how do I choose the features and how do I choose the parameters. If it turns out that it's important for me to preserve something about the unigram probability of bank, I can throw it in as a feature. That is very true.
So the general form that you come to at the end when you take the log, it's not terribly different from the shrinkage where you have a number of different probability values and you shrink them together with individual lambda weights, which need to sum to 1.
I think it's very different.
I think it's different because the feature functions don't have any restriction on what they can be, and the lambdas don't have any restriction on what they can be. And then shrinkage,
They have to sum to 1.
the lambdas have to.
You're comparing the shrinkage to this thing?
Yes.
The biggest difference, I mean, what you said is true, but the biggest difference is this is used to model the log probabilities, not the probabilities. So you can think of the exponential model as some kind of linear interpolation in the log prob domain. The log consists of a weighted linear interpolation of numbers. That similarity is there. But the biggest difference modeling-wise is you're thinking of the log probability as a linear combination rather than the probability as a linear combination. That's a huge difference, and I argue that in many cases it's the appropriate space in which to think of linear combination. The downside is that it's not the log problem that needs to be normalized, it's the probability that needs to be normalized. And therefore, what was very easy to normalize in the normal linear interpolation case becomes very difficult to normalize in the log prob case. Okay, we will come back to this and rehash it and answer more questions next time.